pre-stress concrete, increase of stresses in steel in bonded and unbonded members. When we consider pre-tensioning, in pre-tensioning, pre-stressing force is applied and then concreting is done. After gaining strength, the cables are cut. So there will be a bond between concrete and the pre-stressing force. So pre-tensioning is a bonded member, whereas in post-tensioning, concrete is cast first and no pre-tensioning is given to the cable initially. After concrete is cast by leaving a duct, this is a duct, a space for provision of the pre-tensioning tendon or post-tensioning tendon. Now pre-stressing force is applied after the gaining of strength of the concrete. Now if duct is grouted, then there will be a bond between them, so then it becomes bonded member. If the duct is ungrouted, then it becomes an unbonded member. First let us analyze for a bonded member. Then external load is applied due to dead load and live load. Let us say the bending moment developed is M. Then the increase of stress in tendon, stress in concrete at the level of tendon due to the external load M will be Fc, that will be equal to M by I into Y. Y is at the level of tendon E. Then increase of strain in concrete will be equal to stress by Young's modulus. Since Young's modulus is equal to stress by strain, so strain will be equal to stress by Young's modulus, which is equal to M by I into E into 1 by Young's modulus of concrete. Due to strain compatibility principle, strain in concrete and steel will be same. So increase of strain in steel will also be same, that is equal to 1 M by I into E into 1 by epsilon C, whereas increase of stress in steel will be equal to strain into Young's modulus. Strain is M by I into E into 1 by EC into Young's modulus of steel will be ES, that can be written as ES by EC into M by I into E, where ES by EC is equal to alpha modular ratio. Then this becomes alpha into M by I into E. Say at any level Y, this will be equal to alpha into M by I into Y. Whereas for unbonded members, consider a dx length, then increase of stress in concrete at the level of steel will be, say, Fc, which will be equal to bending moment at that section X by I into at level of steel or at any level can be Y. Then increase of strain in concrete will be equal to stress by Young's modulus of concrete, that is equal to mx by I into y into 1 by Young's modulus of concrete. From strain compatibility, increase of say total increase of length will be equal to integrating, since it is in dx length increases this much, in total length it will be integrating from x equal to 0 to L mx by I into y into 1 by Young's modulus of concrete into, in length will be equal to strain, so strain into dx, so into dx. Now that change in length, that is delta L, let us say, taking all other constant as common, y by I into 1 by c integral 0 to L mx dx. We know strain is equal to change in length by initial length, so average strain will be equal to change in length by initial length, that is equal to y by I into 1 by L into 1 by where E is Young's modulus of concrete, integral 0 to L mx dx. Now increase of stress in steel will be strain in steel and strain in concrete are equal. So this is, if this is strain in concrete, this will also be the strain in steel. So this strain into Young's modulus of steel will give us the stress. So Young's modulus of steel into y by I into 1 by L into 1 by EC, integrating from 0 to L mx dx. ES by EC is given as modular ratio alpha. So alpha into y by I into 1 by L, integration from 0 to L mx dx will be, integration is also called as area, so area of bending moment diagram. So this will be into area of bending moment diagram.